Hello and welcome back. So this time we're going to be talking about Gibbs Energy and work. So Gibbs is kind of the star of the show when we're talking about spontaneity, only because even though what makes a process spontaneous, as we've seen, is that it will raise the entropy in the universe. I think that's the probably the most reliable thing that we can count on is that if it is making the energy of any system more diffuse, then that's going to happen again without having to put any work into the system. But entropy itself is something of an abstract concept. It's a little bit tough to wrap your head around. And it doesn't directly relate to anything that we'd be interested in, like, okay, cool. So if we're increasing the entropy of the universe, what does that mean for how far I can get on a tank of gas? It's very tough to extract any kind of meaning out of that property. So, what Gibbs does, or what Gibbs's energy allows us to do, is to transform that into a kind of energy that we can then compare to other energies that we've already known or seen and apply that to tasks. So that's why we're saying it's Gibbs and work. Okay, so Gibbs energy change, so delta G, is a famous quantity, but what we're really doing is measuring the spontaneity of a process. So measures spontaneity, and it tells us the maximum useful energy available from the system. Okay. System. Useful energy meaning that if all of the energy in the system is spread out equally among all of the different places that you could store energy. So essentially, every molecule is exactly the same temperature. Every part of space is indistinguishable from any other part of space. Then there's really nothing you could do to that system to get it to do work. There's nothing that we could, no way we could say, okay, well, this is going to be our system, the rest is going to be the surroundings, and we're going to see how we can cause it to react or cause something to happen so that we can affect the state of another part of the system. If everything is indistinguishable from everything else, how are we ever going to begin that? The answer is you can't. So this is what ever rising entropy means, is that gradually everything is going to this perfectly flat, perfectly universally symmetrical kind of state that there's really no useful energy available left, or meaning that if it's maximally entropic, that means that we just can't extract any work from it. All of the work that we could have extracted has been extracted, if you like to. Just the universe as a dead battery. So let's just rewrite our equation here. So universe, delta S of the universe is the delta S of the system. Don't know why I keep forgetting that S. Plus the delta S of its surroundings. Okay, and at a constant P, at a P constant, we've already said that delta S of the surroundings is equal to the negative change in enthalpy of the system per temperature. And so we can plug that into our equation. So we have delta S of the system minus delta H of the system per temperature. So now at least we're only measuring things in the system. We don't have to measure the rest of the universe. Just our little part of it will do, and we can still get some information about the change in entropy of the entire universe. But now we want to turn that into an energy. So let's multiply everything through by negative temperature, so that we get negative T delta S of the universe equals negative T delta S of the system plus delta H of the system. Okay, now when we're thinking about units, this is say joules per mole or kilojoules per mole, but we'll just say joules per mole. The entropy is always joules per mole Kelvin. Now we're multiplying it by a temperature, so it's also joules per mole. This is also joules per mole. So now we have, sure, it's in a concentration of energy kind of thing, but they're all going to be essentially energy units. So if we take this term right here, so the negative temperature multiplied by the change in entropy of the universe, and we redefine that as the Gibbs energy of the system. Now we have something that we can kind of use. So we have our delta H of the system, so this is going to be the change in enthalpy minus the temperature multiplied by the change in entropy of the system. And because we want a positive change in universal entropy for a thing to be spontaneous, now if we're going to say at what point is something spontaneous, if the universe change in entropy of the universe is above 0 and delta G is just the negative change of the universe, then we say delta G is below 0. So any negative delta G, any negative Gibbs energy implies spontaneity. And why can we see that? So we say, okay, a positive delta H means that there's heat coming into the system, or the surroundings are getting less without changing temperature. So there's the system's entropy is going down. And if we have a negative entropy of the system, so again, the system itself is becoming more concentrated in its energies, then this term will become positive and the whole thing will be quite positive and it won't be spontaneous. However, if we have something that's giving out a large amount of energy as heat into the surroundings, and it's also becoming more entropic, it's increasing its own entropy at the given temperature, then both of these terms are going to be negative overall. If this, even the entropy term is positive, and we have a negative there, so it inverts it. So this whole phrase becomes negative, and we have a good negative delta G. That's a spontaneous system. So when you think about it in a few examples, it should make sense. So the good one that I think is the easiest to remember is probably going to be like combustion. So it's releasing heat into the surroundings. We're getting a liquid or a solid, or even a gas if we're just burning hydrogen, but we're turning it into more gas molecules. So we end up increasing the entropy. We also increase the heat that's given off, and so the whole thing is spontaneous. Okay, delta G, you'll notice, is a state function because it's made up of other state functions. So reminder, a state function is any that it doesn't really matter how we get there. It's path dependent. Whether we're going to change the enthalpy or the entropy, it doesn't matter. Delta G is delta G, however we get there. So it also means that we'll be able to get a standard delta G for the system that we can use in a Hess's law type arrangement, where we have the delta G of the products minus the sum and delta G standard of the reactants. Okay, so which I think you'll find eventually will be quite useful as well. So let's try an example. So potassium chlorate, an oxidizing agent in fireworks and match heads, sure, undergoes a solid state disproportionation reaction when heated, giving solid potassium perchlorate and potassium chloride. Okay, so first things first, start off with the balanced chemical equation. If you don't remember what all of those things are, first of all, look back in your notes because we definitely mentioned all of these earlier in the course. or just at this point look them up online. And to get a balanced chemical equation, I'll just give it to you so that we can move on. 3KClO4 and potassium chloride as a solid. This is also a solid. Okay, so there's our balanced chemical equation. And remember that the disproportionation just means that it's reacting with itself to come up with a few different products. Okay, so if we want to calculate delta G for this reaction at 25 degrees, we're going to need actually quite a few other numbers because, and you can look this up in a table because again, for any of the thermodynamic values that we would need to calculate delta G, all of their properties, so whether it's the heat of formation or the standard entropy, because of Hess's law arrangements, is just tabulated data. So it might be a good idea at this point to try this question, but try looking up a source that will give you the, we want the standard heats of formation, and we want the standard entropy for all of these reactants. Because what are we going to do for delta G? We're going to have delta G equals to delta H minus T delta S. Delta H we can calculate according to Hess's law, right? And same thing we can do for delta S. So I'd encourage you to do that right away. And I'll just write down the numbers here because I have them. Okay, so for the system, we have 3, so this is for the products first. So this is going to be for the, excuse me, it's going to be for the potassium perchlorate. So 438.8, and this is kilojoules per mole, plus, and 1 of the potassium chloride, negative 436.7 kilojoules per mole, and let's close that off, minus the products, so that's 4 times negative 397.7 kilojoules per mole, and that I'm going to have to make some space, but that's okay. That is equal to negative 144 kilojoules per mole. Okay, and doing the same thing for delta S. We have 3 times 151.0 plus 82.59. Okay, again, this is for the potassium perchlorate and for the potassium chloride, minus the reactants at, okay, 4 times 143.1 joules per mole Kelvin. And this equals negative 36.8 joules per mole Kelvin. Okay, so we have a negative change in entropy, but a very large negative delta H. So it's pushing out a lot of heat into the environment, which is good in terms of spontaneity. But the entropy of the system itself is negative, so we'll have to just see how that balances out. So let's plug those into our calculation. So we want delta G for the system is negative 144,000 joules per mole, minus the temperature, so it's at 25 degrees Celsius, so that's 298 Kelvin, times negative 36.8 joules per mole Kelvin. And this gives us a final answer of negative 133 kilojoules per mole. Okay. So because the Gibbs energy is negative, and strongly negative in this case, we can say that it's a spontaneous process, and we can let it do a certain amount of work. And note the bottom of the page. So if we say that it can also be calculated from the standard Gibbs energy of formation values, Gibbs energy of formation. So that would be if we take for each of the products and reactants. So the Gibbs formation for, let's say, for the potassium chloride is going to be equal to the heat of formation for the potassium chloride minus temperature of the standard entropy. I should stop drawing that little triangle, but that's fine. Standard entropy of the potassium chloride. So we could do that for each of the products and reactants and then just use the Gibbs energy of those same things. You'll see that it works out to exactly the same numbers. So if you have the standard Gibbs values for those reactants and products, then go ahead and use them. Unless you're asked specifically to calculate the enthalpy and the entropy before moving ahead. Okay. So that's where I'm going to stop it for now, and we'll pick it up next time with talking about Gibbs energy and work specifically, and the effect of temperature on how much work we can get out of a process. Okay, so until next time, thank you for watching, and we'll see you then.